Anyway, the reality is that most of us will not heal like coyote when we fall or when we jump off the cliffs. I don't recommend this. And in fact, the challenges of injuries from falls in humans who don't have a fox to repair them is really why I'm here and a big part of my research program. Indeed, falls are a major public health problem. So some quick statistics: in older adults, falls cause over 80% of injury-related hospitalizations and traumatic brain injuries, and about 95% of hip fractures. Most older adults who sustain these injuries will never regain their autonomy and independence from before the fall. So with these sobering statistics in mind, my research vision is to improve the evidence base on how the design and use of assistive technologies, built environments, and everyday tasks affects fall and injury risk, to guide design standards, new products, and best practices across the lifespan. I'm going to talk about two recent and exciting lines of inquiry toward this goal. So I'll start by talking about how handrail height affects balance, recovery in healthy adults. And then I'll talk about how the use of mobility aids and other held objects affects the risk of for head impact from falls in long-term care residents. So to kick this off, I'll discuss some of my recent research and knowledge translation based on my PhD work at Toronto Rehab, where we explored the relationship between handrail height and fall prevention. This work was supported by an operating grant from the Canadian Institutes of Health Research and scholarships from AgeWell and the Government of Ontario. So handrails are common products that reduce the risk of falls as long as their design allows the person to grasp the rail quickly and then effectively stabilize their torso. However, evidence to inform handrail height standards is limited because of the practical challenges of collecting data safely. So this didn't sit too well with my team in Toronto. So here's some of the tools that we actually installed and built and used to explore the relationship between handrail height and balance recovery. So on the left, this is the outside of the laboratory. The giant cube on the top is the lab itself. It's mounted to a hydraulic motion simulator, which allows us to suddenly shake the lab and then destabilize people in a controlled way. On the right, we have the inside of the giant cube with the participant. So this is my dad. He's secured to a safety harness and walking beside a height adjustable handrail. He's excited for the chance to be famous with a different crowd. So to measure grasping speed, we use 3D motion capture and an electromyography sensor on his arm to measure muscle reactions. And to look at grasping effectiveness, we use 3D motion capture, and you can kind of see some markers all around his body. These are the things that are awkwardly taped to him that aren't the harness. And this allowed us to measure torso and center of mass kinematics during balance recovery. So I'll start by walking you through our speed findings. We found no effective handrail height on contact time after balance loss or the onset of upper limb muscle activity, even after controlling for the person's height. So what we took from this is that contact time was not compromised by higher handrails, even though the initial distance from the participant's hands was greater. We took a closer look at individual reach trajectories to understand our contact time findings. So what I have here is some sample motion capture data from one person on the left and group data on the right. So we can see that as handrail height increased, the vertical overshoot, or the peak distance between the person's hand and the handrail, I tried to represent it up here with a stick figure, and it was that property decreased. So what this tells us is that participants compensated for the greater hand-to-handrail distance by reaching more directly. And it's one perhaps counterintuitive finding that really reinforces the need for a detailed look at what's really happening to explain our gross speed findings. Let's look now at effectiveness. So as handrail height increased, peak forward and sideways torso angular displacement decreased. So forward being on the left, sideways being on the right. And what this suggests is that there was a torso control advantage with handrails up to about 40 to 42 inches. So for comparison, up until 2018, the British Columbia Building Code range was 34 to 38 inches. So actually below the handrail heights that enable the best torso control in this population. So to bring these findings back together, higher handrails surprisingly were not problematic from a grasping speed perspective. However, they were advantageous from a recovery effectiveness perspective up to about 40 to 42 inches. This work led to WorkSafe BC raising the upper boundary on their handrail height design range in their guidance for occupational fall prevention. And I'm excited to work with them in the years ahead. This work was also cited in the 2019 Australian Construction Code when justifying the need for handrails on stairs and ramps. I'll transition now to some cool new work that looked at technology for preventing injuries when falls occur, based on my postdoctoral efforts at Simon Fraser University. For this work, we partnered with 2 long-term care homes operated by the Fraser Health Authority, with support from postdoctoral awards from the Michael Smith Foundation for Health Research and Age Well, and an operating grant from CIHR. So my postdoctoral team at Simon Fraser University had collected over 3,400 videos of real-life falls by long-term care residents, had collected videos of over 3,400 real-life falls by long-term care residents based on surveillance footage that was installed in care facilities. This is an ongoing project that has been taking place since 2006. This allowed us to gain high-quality evidence on biomechanical risk factors for falls that would otherwise be impossible to pull from laboratory studies, especially in long-term care residents who really should not be put on robotic platforms to induce falls and see what would happen. So our team coded these videos of falls using questionnaires. So for those who've never used questionnaires for video analysis, what we do is we go through and we characterize things like, what was the person's activity at the time of the fall? Like, were they walking, were they standing, were they sitting, or doing something different? We also looked at whether body parts impacted the ground or other parts of the environment. And we looked at whether residents held objects like walkers or wheelchairs during the fall. We also combined the questionnaire data with injury outcomes to get a sense of what were the consequences in addition to impacts that might have associated with different falling behaviors. So one major finding from this early work was that 1 in 3 falls by long-term care residents involved head impact. So what this suggests is that something is probably going wrong with how well residents can use their arms to stop falls, in the same way that you or I might stick our arms out to avoid hitting our head when we lose balance. So to gain a better understanding of risk factors for head impact in the complex long-term care setting, we asked 3 questions. So first, how often do residents hold or reach to grasp objects when they fall? Second, what kinds of objects do they hold, like mobility aids or cups of water? And finally, how does holding objects affect the odds for head impact? So we were surprised to find that over 2 in 3 falls involved holding objects. So a common assumption in this area is that people are often holding nothing when they fall, and that's what a lot of the research is based on. And we actually showed that this is probably not a good assumption when we look at what happens in real life. We classified objects based on whether they were weight-bearing or non-weight-bearing, because these were likely to have different effects on the mechanics of the fall. So over 50% of falls involved weight-bearing objects, and I've indicated this here in blue. About 11% were non-weight-bearing objects, this is in gray, and about 4% were cases where residents held both weight-bearing and non-weight-bearing objects in this checked blackish pattern here. We also found that residents often continued to hold the objects throughout the fall, with the graphs maintained in over 50% of falls with weight-bearing objects, shown on the, middle here, and in over 70% of falls with non-weight-bearing objects, shown on the right. We also characterized the most common held objects, and these were by far walkers and rollators, and chairs and wheelchairs were the most common, followed by a range of other objects like tables and counters. Finally, we found that when residents fell while holding weight-bearing objects, the odds for head impact were reduced by 2-fold. The outcomes were the best when residents held the weight-bearing object all the way through to landing. And we found similar results for walkers and rollators on their own compared to holding nothing. So in this video, you can see an example of how the resident is using the walker to slow her descent during the fall, and she's able to keep her head from the ground and avoid other injuries. I was personally really excited by this finding because there is a common perception in clinical world that people should avoid using walkers or rollators because of the idea that they create dependence. And instead, we see that even when they fail to prevent falls, they still allow people to fall more safely. This work is recent, and we're disseminating among colleagues with provincial health authorities to help guide best practices for technology use for injury prevention. So I'll talk a little bit about what's next. I'm planning to continue using the tools of biomechanics to understand how the use and design of assistive technologies and built environments alongside movement tasks like walking or standing or grabbing affects fall and injury risk. So I'm currently part of a funded research cluster in aging in place at UBC Okanagan. I'll give a shout out as well to the airborne disease transmission folks. I'm involved in some of their human factors work. Anyways, we currently have motion tracking, force analysis, and muscle monitoring capabilities. And I'm working to supplement that with more exciting tools for inducing balance and falls. I'm also expanding relationships with local care providers, including the Interior Health Authority, WorkSafe BC, and Codes Canada, and the leadership of the CSA Long-Term Care Standards Committee to motivate and provide a path for knowledge uptake for preventing falls and injuries in the community, in care settings, and in workplaces. In particular, I was recently named to the task group on stairs, ramps, handrails, and guards with the National Building Code of Canada as a voting member and fall prevention expert. And to me, this is a really exciting path to continue with translating research findings on balance and falls to change our building codes for a safer world. My work basically will continue to span laboratory and field data analysis. So this includes strengths in mining databases on the circumstances of falls that lead to hospitalizations and other injuries. So that might be useful for people here if you're looking to get data to motivate some of your product development work. And then finally, I'm always looking for partners and collaborators with interests in fall and injury prevention, ergonomics, and assistive technologies in the community and in workplaces. So if this is of interest to you, then let me know. So thank you all for having me today. And I assume we're doing questions afterward. But regardless, I hope to be in touch in the coming weeks. Thank you so much.